So we'll start with that one. I'm going to start by writing my divisor on the outside of my division bar. And notice here that we have no x to the fifth, no x to the third, and no x terms. So I'm going to make sure that I put zeros in those spots. It'll help me kind of keep all my like terms lined up appropriately, and really kind of greatly simplifies our organization for this problem. So that's going to be a big help doing that. So there's my setup. Again, notice that I put those zeros in for the missing terms. So then I'll start by asking myself, okay, what times x squared gives me x to the sixth? And that's going to be x to the fourth. Because 4 times x squared gives me x to the sixth. And if I distribute this across the entire divisor, I get this. And then we need to subtract down. Before I subtract, though, what it's usually a better idea to do is to distribute that negative. So negative of a positive is negative, negative of a positive is negative, and negative of a negative is positive. So now when we go x, you do term by term, so x to the sixth minus x to the sixth is 0. 0 minus x to the fifth is negative x to the fifth. Negative 14x to the fourth plus 14x to the fourth is negative 8x to the fourth. And we'll bring down the next term, and we'll go back to the top. We'll ask ourselves, okay, what times x squared gives me negative x to the fifth? That's negative x cubed. I'll go and distribute that across the entire divisor. Negative x to the fifth minus x to the fourth plus x to the third. Oops, sorry, 6x to the third. And then we'll distribute that negative. So negative of a negative is positive. Negative of a negative is positive. And negative of a positive is negative. So negative x to the fifth plus x to the fifth is 0. Negative x to the eighth plus 1x to the eighth is negative 7x to the fourths. I don't know why I said 8 there. You knew what I meant, though. And then 0 minus x to the sixth is negative x to the sixth. And then we'll bring the next piece down. And we'll go back to the top. So we're going to ask ourselves, what times x squared gives me negative x to the or negative 7x to the fourth? Well, that would be negative 7 squared. So I'll distribute that through. That gives me negative x to the fourth minus 7x to the third plus 42x squared. And we'll subtract down. Again, let's distribute that negative through, so negative of a negative is positive, negative of a negative is positive, and negative of a positive is negative. And we'll go and negative 7x to the fourth plus 7x to the fourth is 0. Negative 6x to the third plus 7x to the third is 1x to the third. 49x squared minus 42x squared is 7x squared. And then we'll bring the next term down. And then we go back to the top. So we're going to ask ourselves, what times x squared gives me 1x cubed? Well, that should be easy to see that that's just going to be x. So I multiply that to the whole divisor. 1x cubed plus 1x squared minus 6x, and then we'll subtract. before we do that subtraction, let's distribute the negative through. So negative of a positive is negative, negative of a positive is negative, and then negative of a negative is positive. So 1x cubed minus 1x cubed is 0. 7x squared minus 1x squared is 6x squared. And 0 plus 6x is 6x. And we'll bring our last term down. And so we'll ask ourselves now, what gives me 6x squared? And hopefully it's easy to see that's just going to be 6. When I distribute that through, come on, there we go. I get 6x squared plus 6x minus 36. I subtract down, distribute through my negative, and I have minus and plus, and that gives me 0, 0, and 0. So at the end, we say that this is remainder 0. So my answer then is just the quotient. Since the remainder is 0, I don't have to worry about anything else. Natalie, did that help?
Yes, it did.
Okay, good. Again, can be a lengthy process, right? That one we had 5 steps to kind of work through, but each of the steps are relatively easy. Usually the hang up is making sure that we distribute our negative and we don't add something wrong or goof up the multiplication along the way. There's lots of opportunities to make one of those silly little simple mistakes that causes things to kind of spiral out of control. So you have to make sure you're being careful and you're being neat while you're working on this so that you can keep good track of everything. But the problem itself, the individual steps are not difficult. It's just kind of making sure you keep on track with everything that can become a little bit challenging. Other questions from the assignment that we would like to talk about? Okay. That's fine. If you guys change your mind, you can always let me know later, and we can certainly come back and talk about some more. But let's go ahead and talk about the new stuff for today. So what we're going to talk about first is a shortcut to polynomial division. And that shortcut is called synthetic division. And like any shortcut in mathematics, the reason you don't get the shortcut first is because it doesn't work every single time. So there are conditions to using this shortcut. Let's write that down. So in order to use synthetic division, we have to have the leading coefficient and the degree of the divisor equal to 1. So if we go back and we look at our homework assignment from last night, we had 3 of these division problems. Number 8, if I look at the divisor, has a leading coefficient of 1 and a degree of 1. So we could do synthetic division for number 8. Similarly on number 9, our leading coefficient is 1 and our degree is 1. So we could do the synthetic division here on number 9. But on number 10, you'll notice that the leading coefficient is 1, but the degree is 2. So we couldn't do synthetic division on number 10 because it doesn't meet the criteria. Now, I haven't shown you how to do the synthetic division yet. We've just talked about when we can do it and when we can't, but that's an important piece of this, right? If you have a tool, you have to know when you can use the tool and when you can't. So just for the sake of example, let's do number 8 here together as an example of how to do the synthetic division. The love of this synthetic division is that you guys already know how to do this. I've already taught you how to do this. And I don't remember you teaching me this. And it's because you didn't know that I was teaching you this when I taught it to you. So this is the problem number 8. I've just recopied this. This is the division problem that we're going to do using this polynomial or this synthetic division shortcut. So the first step, we're going to take the divisor and set it equal to 0 and solve. So that's very easy. The next thing we're going to do is we're going to set up a synthetic substitution, where I'm going to take that solution that we just found, and that's going to be the number that goes on the outside of my synthetic substitution. Set up, and the numbers that will go on the inside are going to be the coefficients from the dividend. Everybody okay with this setup? So it's just almost the exact same as the synthetic substitution setup, right? And now the process that I'm going to do is exactly the same as the synthetic substitution process. So I'm going to begin by just bringing the first number down. And then I'll multiply the number on the outside, that number below, and then write the result in the next spot and add down. Just like we did for synthetic substitution. I'm going to continue doing that. So 5 times 1 is 5. And then if I add down, negative 12 plus 5 is negative 7. Negative 5 times negative 7 is negative 35. And we add down is negative 6. And 5 times negative 6 is negative 30. I add down and it's 0. And we're done. The division is over. And you're looking at me like, I don't see an answer to a division problem here. And it's only, well, that's okay. It's only because you don't know how to interpret the numbers here at the bottom. So each of these numbers here at the bottom is going to tell us something about our synthetic division problem. So we're always going to start by looking at the number at the far right. The number on the far right is always going to be the remainder. The next number is going to be the constant term, and then the coefficient for x, and the coefficient for x squared, and the coefficient for x to the third. So as we move from from right to left, across those numbers at the bottom of our synthetic division, the degree of x just kind of goes up by 1. So it always starts remainder, and then the constant term, and then x, and then x squared, next to third, next to fourth, next to fifth, and goes as long as you would need it to, as long as you have numbers. So using this, we can say that our answer then is 2x cubed plus 1x squared minus 7x minus 6, and since the remainder is 0, we don't have to do anything else. Oops, I already used blue.
Mr. Kulak,
Yes.
for the remainder on like a test or something, if we just put like R and then the number of the remainder, would that be like still acceptable?
No.
Or do we have to do
You must write it as a fraction. You must write it as a fraction.
Okay.
And the reason is that that'll come up later in future courses. Using that format will be quite helpful. So we're going to get used to using that format now.
Would we write it at like hypothetically, if there was a remainder on this question, would we write it as like remainder over 5 or remainder over x minus 5?
Always the divisor. So in this case, it would be whatever that remainder is over x minus 5. Yep, these are good questions. Shall we do another as an example? Probably worth doing that. So let's say we have x to the 6th minus 1 divided by x plus 2. So first thing you should do is check to make sure you can use the synthetic division on this problem. If I look at my divisor, it definitely meets the criteria. Its degree is 1 and its leading coefficient is 1. So I'll set that equal to 0 and solve for x. And I'm going to use that result as the number on the outside of my synthetic division problem. And the numbers on the inside of my synthetic division problem are going to be the coefficients from the dividend. So the first coefficient would be, anybody? Well, I have 1x to the 6th. So the first coefficient should be 1. What's the next coefficient going to be?
Wouldn't you have to keep doing like 0 to x to the 5th until you got down to this 1?
Yes. So we're going to need a 0 for all of these. So we're going to need 5 more zeros. Very good. And then the negative 1. Everybody happy there? So there's my setup. The first step will bring that first number down. Negative 2 times 1 is negative 2. I add down, that's negative 2. Negative 2 times negative 2 is positive 4. I add down, and that's 4. Negative 2 times 4 is negative 8. Add down, and that's negative 8. Negative 2 times negative 8 is 16. I add down, that's 16. Negative 2 times 16 is negative 32. Add down, and that's negative 32. 2 times negative 32 is 64. add down, and that's 63. So again, very fast, right? We did this very long division problem in like 15 seconds, which is wonderful. So again, we have remainder, constant term, x coefficient, x squared coefficient, and so on. So we'd say that our answer is 1x to the fifth, you don't really have to write the 1, minus 2x to the fourth, plus 4x to the third, minus 8x squared, plus 16x, minus 32, plus my remainder over my divisor. Which is a fabulous shortcut. Look at how much less space that takes up than a long division problem. Look at how much faster that is. So many fewer opportunities to make an arithmetic mistake. Very, very efficient, very fast. Quite a useful method. Particularly in second semester when we continue on in this chapter and we start talking more about factoring and solving, dividing by these little linear polynomials is going to be kind of a key component to our technique. So we'll use this a lot in the second semester when we start factoring some larger polynomials. So we're going to get a lot of use out of this. It's a quite a useful shortcut and a very, very valuable technique. The shortcoming of it, though, is can't use it every time, right? The divisor has to be in that particular form, having a leading coefficient of 1 and a degree of 1. Okay. We'll start talking about some factoring topics now. So we're going to talk about 3 specific factoring patterns. So the first one is the sum or difference of 2 cubes. So the sum of 2 cubes factors like this. And the difference of 2 cubes factors like this. So we'll do a couple of examples and getting comfortable using these 2 factoring patterns. So I have, as an example, 8x cubed minus 27. When I see this initially, I notice that I have 2 terms, and I have only 1 term as an x on it, and it's an x to the third. So it's a good candidate for being able to use this difference of 2 cubes. So what I'm going to try to do is rewrite 8x cubed as something to the third power. Well, I know 8 is 2 times 2 times 2, right? 2 times 2 is 4, and times 2 again is 8. And x times x times x is x to the third. So 8x to the third is really the same thing as the quantity 2x to the third. And then I notice 27 is 3 times 3 times 3. 3 times 3 is 9, and 9 times 3 is 27. So I can write both terms as something cubed. So looking at my factoring pattern here, I have something that looks exactly, oops, it's supposed to be a 3. I have something that looks exactly like that. In this case, my A would be 2x, and my B is 3, right? So to factor this, all I need to do is plug in my values for A and B into the other side. So I have 2x minus 3 times 2x squared plus 2x times 3 plus 3 squared. And I can simplify things there a little bit. 2x squared is 2x times 2x, so that's 4x squared. 2x times 3 is 6x, and 3 squared is 9. Any questions on that one? Okay. Let's just do one more example to make sure we got it. So let's say we have x cubed plus 125. So again, I see something cubed plus a constant, or an x cubed, something with an x cubed on it, plus a constant. This is a good candidate for a sum of two cubes. It's pretty easy to see that x cubed can just be written as x cubed. And 125, well, let's think. 5 times 5 is 5, or 5 times 5 is 25, and 25 times 5 is 125. So that's going to fit our sum of two squares factoring pattern. So now I can just plug in my values for A and B into my pattern. So I have x plus 5 times x squared minus x times 5 plus 5 squared. And if I clean that up, I get x squared minus 5x plus 25. The only thing to be cautious about here is taking note that, like, not everything at first glance is something, well, let's make it a little bit more challenging to see, is a difference or sum of two cubes. For example, if I have x to the third plus 6, well, x to the third is no problem. But 6 I can't write as something cubed, or at least not a whole number, right? I know 1 cubed is 1, and 2 cubed is 8. So 6 cubed is something in between. So this is not factorable, because there's not going to be a whole number for me to do that. I just wanted to make sure that we're clear that you can't always turn something into a sum or difference of two cubes. You have to have both pieces able to write as something cubed. Any questions on using this particular factoring pattern so far? Okay, very good. The next one we're going to talk about is the difference of two squares, which we've already used in the previous chapter. So this one should be pretty easy to deal with, but we can extend using this factoring pattern beyond things that are strictly quadratic. So for example, let's say I have x to the fourth minus 16. Notice x to the fourth is not a quadratic polynomial, right? This is a degree 4 polynomial or quartic polynomial. But just like I did for the cubes, I see an even exponent on my x minus a constant. So this is a good candidate to be a difference of two squares. So I need to think about x to the fourth as something squared. Well, I know x squared times x squared is x to the fourth. So x to the fourth could be x squared squared. 16, well, that's easy. That's 4 squared. So this fits the pattern. So I can now just plug in my values for a and b, where a is x squared and b is 4. And you might think, okay, we're done. Well, look a little bit closer. X squared plus 4, I know that that's not factorable. But x squared minus 4 is another difference of two squares, right? That would have been something that we handled last chapter. So the x squared plus 4 can just stay the same, but x squared minus 4, I need to continue factoring. Okay there? Okay. Let's do another example. Let's say we have x to the sixth minus 64. Well, again, I have an even exponent on my x minus a constant term, so this would be a good candidate for a difference of two squares. So I need to write x to the sixth as something squared. Well, I know x to the third times x to the third is x to the sixth, so I can write x to the sixth as x to the third squared. 64 is just 8 squared. So my a is x cubed, and my b is 8. So I can refactor this as x cubed plus 8 and x cubed minus 8.
Wait, Mr. Kulik, I thought you couldn't I thought that like 3 times 3 was 9. I thought that was the way that we were doing it.
So when you multiply polynomials, you add the exponents?
Oh, okay.
Okay. Right, because if you think about x to the 6, it's just 6 x's multiplied together, right?
Yeah, okay.
Okay. So just, again, remind yourself of what an exponent means. If you ever are confused, like, do I multiply or do I add the exponents? If you're like, okay, x to the 6 is just 6 x's, so that's definitely, we're definitely talking about adding, right? All right, so you might think you're done here, but look a little closer. X cubed plus 8, x cubed minus 8, both of those could be difference of, or sum of two cubes, right? So they both work. I notice here that a is x and b is 2. And similarly here, a is x and b is 2. So when I use the sum of two cubes factoring pattern, I have x plus 2 times x squared minus x times 2 plus 2 squared. So that's coming from this one. And then when I do the difference of two cubes, I have x minus 2 times x squared plus x times 2 plus 2 squared. So that came from this one. And then if I clean things up a little bit, x squared is just x squared, x times 2 is 2x, and 2 squared is 4. So there's that. So again, with these differences of two squares, we have to be a little bit careful to check to see if there's more factoring that we can still do after we're done. Okay. And then the last technique is things that are in the quadratic form. So for example, if we have, say, x to the fourth plus x squared minus 6, that's an example of something that's in the quadratic form, because I can write this as and if we make a little substitution, it's very obvious now that what we really have is just something quadratic, right? So if I factor y squared plus y minus 6, that's something that I could use one of our factoring shortcuts on. The two numbers that multiply to give me negative 6 and add to give me 1 are positive 3 and negative 2. And then we'll make our substitution back in. So we remember y is equal to x squared. And then we would just need to check to see if these could factor anymore. The first one obviously doesn't because it's x squared and with an addition. The second one doesn't either because it's x squared minus, but it's not a perfect square. So this is as far as we could go. Okay with that one? Let's do another. Okay. So I have x to the sixth minus 9x to the third plus 8. So again, this looks like it could be in the quadratic form. So I can rewrite x to the sixth as x cubed squared. Right? And again, what I'm looking for here is that after I rewrite the first thing as something squared, that it matches the variable in the other one, right? The exponents have to match like that. So we'll make our substitution. That y is going to be x cubed. But now we're left with something that should be easy to factor. Oops. We just need two things that multiply to give me 8, and then add to give me negative 9. Well, that would be -8 and -1. And then we'll plug our x cubed back in for y. But we're not done here. Take a close look at what we have. Both x cubed minus 8 and x cubed minus 1 are differences of two cubes, right? So we can continue going. So here, my a is x and my b is 2. Here my a is x and my b is 1. So that's me doing the difference of two cubes for the first one. And there's my difference of two cubes for the second one. And then we'll just clean some stuff up here.